these are two neurons. They're doing their thing, which is learning. What exactly is that?
There are 4 main models that help us understand learning, and it'll be a lot easier to understand them once we dive in and actually see them happen. The first is Hebbian learning. The second, Anti-Hebbian learning. The third, and I always get this wrong, spiking time domain plasticity. The fourth is backpropagation with a loss function. With that, let's take a look how it behaves.
One quick note, if you want to find out about these little noodly things called neurons, check out this short above. Now, Hebbian learning. Named after Donald Hebb and the topics covered in his 1949 book, The Organization of Behavior. The actual quote from this book is this, which, when I first encountered it, it was shortened to the meme, neurons that fire together, wire together. And that really is correlation. Like, they need to sync in time, A and B in sync. And that will cause them to want to grow together. Left and right, firing in sync will make growth happen. These ridges that run along the neurons, they're called synapses, and they're how they do their learning. Learning can be strengthened by growing new branches, new synapses, or even make the synapses stronger. So let's see these two neurons fire together and new synapses strengthen. And that has an interesting effect for the neuron in question. It contributes to how it fires. This is learning. There's something correlated going on here. The purple and the orange, they're related in time. So the orange wants to grow to it so that the purple can contribute to the state of the orange. They're similar, so why don't you have your neighbor tell you about it? And if you watch, you can see the response persist. It's learned. As we look at the bigger brain, there's many different neurons. So this idea of growing to things that are firing together, that are correlated in time, that you can learn from and contribute to what you're firing to, is strong because it helps bring order to the snaggle of noodles. Let's take a look at anti-Hebbian learning as well, which is the opposite. It's almost the anti-learning. We need another neuron, though, something to be out of sync, something to unlearn. And how that happens is we can weaken synapses, lose synapses, or even prune entire branches. And as the neurons fire, you'll see that the one in the back is out of sync with the purple and the orange. They're less correlated in time. And we can have the red neuron back away and make physical separation from the purple and the orange, effectively making that physical separation into concept separation, effectively forgetting anti-learning. Spike timing dependent plasticity is a version of Hebbian learning, one where if you looked closely, you'd notice there's something wrong with the Hebbian example before. The inputs, they're well synced, but what happens at the output, it doesn't quite make sense. We don't just need learning to happen when things are perfectly coincident. We actually want something to learn from what happens before it's ready to react. What informs what's going to happen next? Neurons use trains of spikes to do this. If they're both perfectly in sync, they neither can get any clues about what's going on in the world. But if we shift the lower one, B, out a bit, A gets a clue on what to do. And we can see this in the updated simulation here. If the purple fires just a moment before the orange, it gets a bit of an influence on what orange is about to do. It informs what's going to happen. Now orange doesn't need all of its inputs to fire. It can rely on purple as well. It's learned a new relationship of causal effect. Backpropagation with gradient descent over a loss function. This is the biggie. This is the one that ChatGPT uses, Gemini from Google, and all of the big names that you've heard of. But I've drawn 10 neurons, but you really could have millions or billions. I also need to bring back a trusted friend, the tabby cat from the machine vision video, so we have an input up the stack of neurons. It flows through the stack and responds in different ways by its connections similar to what we've learned about in reacts. If you have put in a cat, you might see a tabby cat based on the activity of that last rightmost neuron. Each connection has a weight, a strength, amount of synapses that it links to the others. We've learned a few methods: Hebbian, Anti-Hebbian, spike timing, dependent plasticity, but what do you do on computers? These are all organic methods. Well, you reduce a neuron to a point, its connections to a weight, W. And you have to figure out some way to set those weights. And that's really the trick here. We need to flip it around and start with the answer, a little a priori. We predict tabby cat, and if we just run our model, it might be kind of random and be really wrong. So we need to run the model backwards to optimize that loss function. Change those weights random-like and see if that loss between what you predict and that cat that you put in reduces. That's called gradient descent. You follow the loss down. This takes a gargantuan amount of compute. And that's each time. We need to iterate through this many times to try to get the loss low. And that's really computer heavy, and it's not real time. Hence all the NVIDIA GPUs. And that's it. That's what backpropagation is. An offline version to try to get the input and the output to settle by propagating backwards and reducing the loss between the two. It's strange and very different from the first three models we talked about. So hopefully that points at something where there might be, even though ChatGPT is awesome, a lot of room for future development.
Let's recap. So you've seen neurons do what they do, which is learning. And there are many theories about how that's done, but no one knows for sure. The four we looked at that should make sense after seeing them are Hebbian learning, Anti-Hebbian learning, spiking time domain plasticity, backpropagation, and there are many more. One of my favorites is network plasticity. The ability for a neuron not only to change the strengths between the neurons, but actually grow an entirely different arbor. But that's a topic for a different video. So until then, hopefully this helped. Stay curious and keep creating. Cheers.